G'day! In the last video we worked out formulas for sums of powers. For example, we want the sum of the first n squared numbers. There's the formula for the powers of 2 from 1 squared plus 2 squared plus 3 squared all the way up to n squared. Well, it turns out the formula for that is a cubic polynomial, 1/3 n cubed plus 1/2 n squared plus 1/6 of n. And we should derive the way to get all these formulas, the sums of any powers you like. Great, grand, and good. But then at the end of the last video, I did something wild and wacky. I showed a sort of pseudo integration technique that lets you go from one formula to the next and you just crank them out really swiftly to go from one to the next, easy peasy, to do this wild, weird technique. Now, just to get that technique back in our heads, it went as follows. Suppose you know one formula. In fact, I do know the sum of the first n zeroth powers. 1 plus 1 plus 1 plus 1 n times adds up to n. So to go from, say, the sum of the zeroth powers to sum of the 1th powers, multiply what you've got so far. So if I've got n, multiply it through by the next number you want, 1. 1 times n is still n. And then integrate with respect to n. But ignore the plus c's. I mean, why not just ignore them? Okay, there'll be half of n squared. Okay, great. And then add an n term with some coefficients so that both coefficients add up to 1. Half plus something is meant to add up to 1. Oh, half. Half n squared plus half n must be the formula. And look, it is. Grand, grand, and good. And to go from that formula to the next one, okay, so to go from P1 to P2, multiply through by 2 this time. Okay, multiply through by 2 gives me n squared plus n. And then just integrate sort of in a very sort of loose way. Okay, the integral of n squared plus n will be 1/3 n cubed plus 1/2 n squared. And don't write plus c's, just don't bother, don't bother. Oh, but do add something times n so these coefficients add up to 1. 1/3 plus 1/2, that's 5/6. So to get to a full total of 1, I need 1/6 there. And lo and behold, that's my formula for P2 of n. And keep going and keep going. This machinery will crank out all the formulas correctly. And it's weird and wild and mind-blowing, and the question is, why does that work? I left that as a mystery at the end of the last video. So what I need to do now is prove all that for you. And this is going to be hefty. This video is not for the faint-hearted. We're going to get to some serious mathematics. In fact, the mathematics I'm going to do today is based on the work of these two fabulous gentlemen. A German mathematician by the name of Johann Faulhaber, who lived at the turn of the 17th century, and then Bernoulli, who also lived a little bit later than him. They actually developed a very nice way to present all these formulas together that then I can actually use to prove this wild and wacky integration technique that it actually works. But it's going to take some serious calculus and some serious work. So what I'll do next is actually list all the things we're going to use from calculus theory, and then I'm going to go through and do the work. It is going to be long and arduous, and hopefully will actually make sense if you want to persevere all the way through it. I'm going to explain it for sure. All right, so let me clean the board and give you the list of all the maths I presume we know. Alright, here's all the stuff I presume we're comfortable with. We have the various formulas for the sum of powers, and we did observe in the last video that every formula, except the very first one, is a multiple of n, and is also a multiple of n plus 1. I use the fact that all these formulas, once we get past the first one, is actually a multiple of n and a multiple of n plus 1. Okay, got that from the last video? We do actually know that one. I assume we're familiar with a geometric sum. 1 plus x squared up to some power x to the n actually is x to the n plus 1 minus 1 all over x minus 1. Hopefully we're comfortable with that formula. In fact, you can check it's true by multiplying the left-hand side by x minus 1. You'll see a lot of cancellation goes on, and what will survive is x to the n plus 1, take away 1. Great. I'm also going to assume we're very familiar with the binomial theorem. To expand a plus b to some kth power, you get all the standard combinatorial coefficients coming out with powers of a and powers of b. So there's the binomial theorem. We'll see that appears in the work I'm about to do. And the real calculus we need is actually Taylor series. We're going to see we've got a nice function that can be differentiated as many times as you want, then there's a good hope it could actually be represented as a series. F at naught plus f primed at naught, x over 1 factorial, plus f double primed at naught, x squared over 2 factorial, plus f triple primed at naught, x cubed over 3 factorial, and so on and so on. And I guess naught is another word for 0. I'm stuck between British English and American English. But I assume we know that Taylor series can exist in many nice examples. In fact, here's one very nice example. we know that the Taylor series of e to the x, that assuming we know, is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on. In fact, that's the key one we want to use today. So these two fabulous gentlemen actually realized that was a lovely segue into getting sums of powers formulas. So let me show you how we can use this Taylor expansion of e to the x to get to formulas like this. Whoa. Okay, so here's the clever entry point into matters. Let's look at this sum. 1 plus e to the x plus e to the 2x plus e to the 3x, and so on and so on and so on down to plus e to the n times x. Let's look at this sum two different ways. Now, I just mentioned Taylor series. Let's actually do the Taylor series way right now. For example, this sum really equals, well, 1 is just 1, not very exciting. But e to the x is a 1 plus an x squared on 2 factorial plus an x cubed on 3 factorial, and so on and so on and so on, infinitely long sum, plus e to the 2x, another infinitely long sum. In fact, it's this sum, but now where I see an x, I'm going to have a 2x. So this will be plus 1 plus a 2 times x plus a 2x squared, that's 2 squared, x squared over 2 factorial plus 2x cubed, that's 2 cubed x cubed over 3 factorial, and so on and so on and so on, plus e to 3x. Okay, now it's going to be wherever I see an x, put a 3x. 1 plus 3 times x plus 3 squared, x squared on 2 factorial plus 3 cubed, x cubed on 3 factorial, and so on and so on and so on. And keep doing this, keep doing this, keep doing this, all the way down to the last one, 1 plus nx plus n squared x squared over 2 factorial plus n cubed x cubed on 3 factorial, and so on and so on and so on. My pen's getting low, not good. All right, great. So there is a very long way to write out that sum, but here's what I love about it. Look at this. Right there, I've got 1, 1, 1, 1, 1. N ones. Here I've got the coefficients being 1x, 2x, 3x up to nx. The sum of the 1 up to n is the coefficients. Here I've got, the sum of all the squares. I can go like 1 squared plus 2 squared plus 3 squared all the way down to n squared as the coefficients. All the way along. In fact, here's the sum of the cubes as the coefficients. So I can see, if I look at it this way, I've got that 1 at the top, plus I've got sum of n1s, p0 of n, plus I've got the sum of the 1 up to n times x, plus p1 of n times x, plus the sum of 1 squared, 2 squared, 3 squared, all up to n squared times x squared over 1, so p2 of n, x squared over 2 factorial, plus p3 of n, p3 of n, x cubed over 3 factorial, and so on and so on. There's all the cube numbers multiplied by x cubed over 3 factorial. Beautiful. I can see that this sum actually is connected to all our formulas. Whoa! Whoa! In fact, that looks like its own little Taylor series. So maybe if I play with this fellow right here and look at its Taylor series and then compare coefficients, I'll have now formulas for each of these individual sums of powers. Great! So let's do that. So this middle stuff can go away. Let me now play with this formula second way. Well, if you look at this, this is really just 1 plus e to the x plus e to the x squared plus e to the x cubed all the way up to e to the x to the nth power. Oh, it's a geometric sum. So the geometric sum says this will be, the next power, e to the x to the n plus 1 minus 1, all over the original thing, minus 1 on the bottom. Beautiful, beautiful. So this is really e to the n plus 1 times x minus 1 over e to the x minus 1. So I guess we have this equals all that. Okay. So what I need to do now is, now that I recognize that all this is actually just that, I need to work out the Taylor series of this beast and compare it to that, and I should be good to go. All right, so let's keep going then. I have a feeling this board space is going to get tricky. Maybe what I'll do, actually, let me clean the board. I'll write this at the top, and then we'll go from there. Back in a moment. Okay, so here's what we've got so far. We've got this great big infinite sum that involves the sums of powers that we want equals this expression right here. If I think about this backwards, actually, I can say this expression here turns out to equal this infinite sum, which kind of looks like a Taylor series in its own right. In fact, I can say, if I were to work out the Taylor series of this particular weird-looking function, I must get that expression right there. which gives us a plan to move forward. Let's work out the Taylor series here, and then we can compare coefficients. The coefficient of x to the k in the Taylor series must match the coefficient of x to the k in this series. It must be pk of n divided by k factorial. Bingo! It might give us an actual formula for pk of n then. Brilliant, fabulous, we've got a way to move forward. Except there's one other thing that could be a little bit off. I mean, notice at the beginning here, the constant term here is 1 plus p naught of n. All the rest about directly pk of n's, but this one is off by 1. So when we compare coefficients, warning, when we do the very first term, we're off by 1. So when we try our formula and it doesn't work for k equals 0, it's bet it's going to be off by 1 because of that very point right there. So if things are off by 1 at the very beginning, don't panic. It makes sense. It should be off by 1 at the very beginning. All right, so that's our mission. Let's work out the Taylor series of this. Now, the Taylor series means take the derivative of this thing over and over again, put in x equals 0s, and off we go. But that seems awfully hard. In fact, we know some stuff. We know the Taylor series of the top line is basically e to the x stuff. We know the Taylor series of the bottom line really is e to the x stuff. So maybe if I just write the Taylor series of the numerator and the Taylor series of the denominator, something will naturally fall into place. Let's just try it. Let's try it. So the numerator, I know that's e to the x stuff. So it's actually e to the n plus 1x must have Taylor series 1 plus n plus 1 times x plus n plus 1 squared x squared over 2 factorial plus n plus 1 cubed x cubed over 3 factorial, on and on and on, and then take away 1. Take away 1 at the end, but I might as well take away that 1 from the beginning. Great! The Taylor series of this is 1 plus x squared on 2 factorial plus x cubed on 3 factorial, and so on and so on. Take away 1 from the end, might as well take 1 from the beginning. There it is. Great. All right, that's looking a little bit scary. Can I make it look less scary? I can see one tiny thing I can do. I see there's a common factor of x on the top, there's a common factor of x on the bottom. Maybe I'll just take out a common factor of x on both top and bottom. That will leave behind n plus 1 plus n plus 1 squared x over 2 factorial plus n plus 1 cubed x squared over 3 factorial, and so on and so on and so on. Pen's starting to run out. Divided by x here, we'll leave a 1 plus an x over 2 factorial plus x squared over 3 factorial, on and on and on and on. Okay. All right, so let's be very clear, just to remind myself, this really was this top line, e to the n plus 1 times x minus 1, and then we divided everything by x on the top line, and this bottom line, I have to change pens, forgive me, this bottom line really was e to the x minus 1, and then we divide everything by x. So very clear, the bottom line is this, and the top line is that. All right, okay, all right. Well, this is actually confusing. This is confusing because I don't want any bottom line stuff. I want just a Taylor series on the top line. I don't want any Taylor series stuck in like denominators of fractions. That is annoying. But I do have a Taylor series on top. Let's keep this and then figure out what to do with that later on. Let me write this as, okay, it really is this Taylor series on this top, which is n plus 1 plus n plus 1 squared x over 2 factorial plus n plus 1 cubed x squared over 3 factorial. Keeps going up. Let me go up to the k's. N plus 1 to the k plus 1, x to the k over k plus 1 factorial, and on and on and on. And then I'm going to times by, I guess, 1 over that. Times by 1 over that. All right, I've run out of room on the board, but let's take that Taylor series on the top, and let's not work with that Taylor series. That's really then gets times by 1 over that. Oh, what is that? That's that. 1 over that is x over e to the x minus 1. All right, so what I've really got going on here is, all right, this series here really is just a series I know times this weird function, All right, okay, so what I need to do is play with this part and see if I can actually modify that by multiplying by it and compare it to that. All right, I'm not giving you hope yet. It just seems a bit weird. I admit this is weird, but let's keep our cool. In fact, this is what Bernoulli and Faulhaber did. They actually kept their cool and said, all right, before I do anything hard, like the actual hard calculations, this is just a function. It is going to have some Taylor series. It's going to be something like a number plus some number times x plus some number times x squared over 2 factorial plus some number times x cubed over 3 factorial. In fact, it goes all the way up to some number b to the k, x to the k over k factorial, on and on and on. there'll be some Taylor series. And that'll be this Taylor series of this thing upside down, x over e to the x minus 1. So you could actually work out these numbers. It'll have a Taylor series. This would be that function at 0. This would be the derivative of that function at 0. This would be the double derivative of this function at 0. You could actually do that. Now let me just do one of them, because actually there's a little bit something annoying here. b0 is actually the value of the function at 0. But if I put in x equals 0, I get 0 over e to the 0, 1 minus 1, 0 over 0. Doesn't make sense. You realize, oh, that's problematic. That's problematic. But remember, this is really, here's e to the x minus 1 over x. So, whoa, this is really 1 over this. Here's this expression, 1 over that, and I can actually, once I cancel out the x's, I can see, oh, I can put in x equals 0. I can see when x is 0, I get 1 over 1 plus 0, 0, 0, 0, 0. Bingo. That's actually 1 over 1 that has the value 1. So actually, even though it doesn't quite look like I'm allowed to put x equals 0 in right away, well, if I think of it this way, oh yeah, I can put in x equals 0, it's fine. Or if you like, you can do L'Hopital's on this, I actually can define this at x equals 0, all is good and grand. Now, if you have the patience and it's miserable, you could take the derivative of this and work out the value of the derivative at 0, and you'll get the value of b1. Turns out to be negative 1/2, if you have the patience. You could then take the double derivative of this. Miserable, but you could do it, then put in x equals 0, you'll get that b2 is 1/6. And then you could do it again, take the triple derivative of this. It would be truly miserable, and then put in x equals 0, you could do it, and you'll get that b3 is actually 0. You could actually work out these numbers. It'd be a terrible way to do it by doing this directly, but you could. In fact, we'll get to these numbers another way. I can show another way how to do this at the end of this video. But for now, we know these numbers can be gotten. Bingo, there's some Taylor series. I'll keep it abstract right now. Actually, people call these numbers the Bernoulli numbers, because Bernoulli was actually playing with these things for sure. But actually, Bernoulli gives credit to Faulhaber for these numbers. So Bernoulli was thinking of these as Faulhaber numbers. Okay, there we go. All right, so right now, we know our infinite sum that involves things we want equals this infinite sum times that infinite sum, and the second one is kind of abstract. That's okay, we'll keep it abstract for now. Alright, so, but what I really want to do is compare this. If I were to multiply this out, these two things out, and compare it to that, I have to compare what's the constant term, what's the number in front of the x term, what's the number in front of the x squared term, and so on and so on. So I want to look at the coefficient of x to the k, the coefficient of x to the k, the general kth term. If I were to expand this out, I'll get something about lots of powers of x, collect all the like terms of x to the k, whatever number goes in front of it, something times x to the k is the coefficient of x to the k. And it must match the coefficient of x to the k up here. And what's the coefficient of x to the k up here? It'll actually be the kth summation formula divided by k factorial. So when I get this is equal to something, if I multiply all this out times x to the k, that's the coefficient of x to the k. Bingo! I basically have a form for all I want. So let's do it. What is the coefficient of x to the k in all this? All right. Whoa. All right. Okay. So let's see. If I were to multiply that by that, I need to look for all the x to the k terms. I get it by doing a constant number here times the actual x to the k term up here. So I'm going to write it all out. It's going to be beastly. I'll get a b0. I'll get an n plus 1 to the k plus 1 and a k plus 1 on the bottom, k plus 1 factorial on the bottom, times x to the k. Or I could take this x term and multiply by the 1 less, by the x to the k minus 1 term. X times x to the k minus 1 will give me an x to the k. So plus I get a b1, and 1 less would be, over here, n plus 1 to the k over k factorial. Or I could do the squared term, b2 over 2 factorial times x squared times the 1 2 less, which would be n plus 1 to the k minus 1 over k minus 1 factorial. And I keep going up, the thirds, fourths, all the way up to this term, x to the k times, I guess, that constant term, plus bk over k factorial, that's it, times n plus 1. Whoa! If I were to multiply that by that and look at all the x to the k stuff, there's all the x to the k stuff, excuse me. All right, great. Great, that's not looking fun. Okay, but let's keep going, all right, let's keep going. I'll erase all that, because what I really want is a form for pk of n. I want to multiply through by k factorial. Let's multiply through by k factorial. So pk of n, let me do this out. Multiply through by k factorial. I'll get a b0, k factorial over k plus 1 factorial, 1 over k plus 1, n plus 1 to the k plus 1. Times k factorial, plus b1, no numbers, 1, I'll just write, n plus 1 to the k. Plus multiplied by k factorial, b2. What do I get for k factorial? I get a k on the top and a 2 factorial on the bottom, and n plus 1 to the k minus 1. Keep going, multiply by k factorial, I'll get a bk times 1 times n plus 1 to the 1th power. Okay, great, great. There is a formula for my sum of powers. Ugh. All right. Not looking friendly. Not looking friendly. It looks abstract. What are these Bernoulli numbers? But let's keep going. Let's keep going. Why not? Next inspired thing to do. Okay, these gentlemen were just doing inspired moments after inspired moments. That 1 over k plus 1 is annoying. Let's pull out a factor of 1 over k plus 1. This equals 1 over k plus 1. All right, here goes. Pull it out. Now it's going to get really messy. b0 times 1 times n plus 1 to the k plus 1. Plus, take it a k plus 1 on the bottom, means I'm going to leave a k plus 1 on the top. b1, k plus 1, n plus 1 to the k. I'll write down here. Pull out a k plus 1 from the bottom, because it's going to be k plus 1 on the top. b2, k plus 1 times k over 2 factorial, n plus 1 to the k minus 1, plus dot 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 dot, give myself a bit more room. Pull out a k plus 1 from the bottom, because it's going to be k plus 1 on the top. bk, k plus 1, n plus 1 to the 1. K plus 1, n plus 1 to the 1. Bingo. Hopefully that's still on the screen just. All right. Because now we're on the true magic moment. This is truly magical. Because you can't help but notice some of these middle terms. K plus 1 times k over 2 factorial. That looks like k plus 1 factorial divided by 2 factorial divided by k minus 1 factorial. That is the binomial coefficient k plus 1 choose 2. This is k plus 1 choose 2. In fact, this k plus 1 right here is k plus 1. K plus 1, we write k plus 1 choose 1. This 1 right here is really k plus 1 choose 0. And let's keep going along. This k plus 1 here, I'm going from 0 to 1 up to 2. I'm climbing up. So I could think of this as k plus 1 choose k. That will give me k plus 1, which was what I erased there. Wow! But then you look at this, 0, 1, 2, up to k, but we're doing k plus 1 choose something. It's like I'm missing a term. So let me actually write out the missing term. Let me rewrite this all again. This is really 1 over k plus 1 times b0, k plus 1 choose 0, n plus 1 to the k plus 1, plus b1, k plus 1 choose 1, n plus 1, the 1 less, plus b2, k plus 1 choose 2, n plus 1 to the 2 less, k minus 1, plus dot 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 dot, plus all the way along to this one, bk, k plus 1 choose k, n plus 1, plus I feel like I'm missing b to the k plus 1 choose k plus 1, n plus 1 to the 0, 1. I feel like I'm missing that. But I'll write n plus 1 to the 0, why not? N plus 1 to the 0. I feel like I'm missing that, so I just put it in. But the trouble is I can't just willy-nilly put it in. I better cancel out having put it in. So let me subtract that term as well. Minus bk plus 1 times 1 times 1. Minus bk plus 1 will do. 1 over k plus 1 times that. And you think, okay, James, where are you going with this? You spent like the last 40 minutes doing nothing but this messy algebra in an abstract way. But look at this. Here's a truly inspired moment. Let's be naughty. Let's be naughty. Let's really use bad notation. Instead of writing bk as though the little subscript k, let's write a superscript k as though it's like a power. So b1, think of it as b to the 1. And b2, think of it as b squared. But no, don't call it b squared. Just think of it as b to the 2. b2 is b2. Because if you're going to do that, b to the 0, b to the 1, b to the 2, b to the k, b to the k plus 1, then you see this is exactly the binomial formula. It's as though we're expanding a binomial in n plus 1 and b's to the k plus 1th powers. N plus 1 plus a b to the k plus 1th power, and then we've got this final little correcting term at the end. Turns out this formula, if we allow ourselves to be naughty and write superscripts instead of subscripts for our b's, pk of n is 1 over k plus 1. It's n plus 1 plus b raised to the k plus 1 power minus b to the k plus 1. Whoa! Whoa, whoa, okay. Now I don't actually have all the numbers b's in our head, but here's the thing. This is stunningly beautiful. The sum of the first kth powers, 1 to the k plus 2k plus n to the k, is essentially of the form n plus 1 plus a series of numbers, k plus 1 minus b to the k plus 1, all divided by k plus 1. There is a stunning formula. An absolutely beautiful formula for the sum of the powers. I don't know what the b's actually are. All the b I truly know right now is that b0 is 1, and I told you some other values, but I just told you them. Right now, all we know is that b0 is 1. Whoops, b0 is 1. And if you do this formula k equals 0, you'll find that actually we're off by 1, just as we expected. But after k equals 0, then it actually is giving us the formulas for the sums of powers. So, all right. Let me pause now, and I think I have to change my batteries. I've been prattling on for a very long time. Let's play with this. I'll show you how it works, and then finally prove that weird, wild, wacky integration technique. All right, I'll be back in a moment. Okay, so here's a version of the famous Faulhaber formula. Let's get a feel for it first. Suppose I want the sum of all the 1th powers. All the, 1 to the 1 plus 2 to the 1 plus 3 to the 1 all up to n to the 1. Sum of the first n counting numbers. Now, according to this formula is, okay, I want p1 of n. Please do, 1 plus, k is 1, so I want squared. I want n plus 1 plus b squared minus b squared all over 2. Okay, great. Well, I don't really mean b squared, because b to the superscript 2 really means the second Bernoulli number, which I told you is 1/6. So I'll trust this for the moment. Okay, so what I do here, so let me expand this out. So this will be, okay, n plus 1 squared plus twice n plus 1 times b to the 1th power plus b to the 2nd power minus b to the 2nd power, well, not really b to the 2nd power, I mean b2, divided by 2. Okay, so they cancel, no worries. And what am I left with? I'm left with n plus 1 squared. So it's n squared plus 2n plus 1. B to the 1 is negative a half. So 2 and negative half minus n minus 1, all divided by 2. N squared survives, n squared plus an n. Ones cancel out, divide by 2. Yep, half n squared plus half n. There it is. Great. Let's check the formula for p0 of n. Why not? Let's do that one. P0 of n would be one more. So it would be n plus 1 plus b to the 1th minus b to the 1th all over 1. That would be technically n plus 1 plus b to the 1th minus b to the 1th all over 1. B to the 1ths cancel, that's n plus 1. But I'm off by 1, which is what I expected, to be off by 1. At the very beginning, we'll be off by 1. Good, grand. So there is the famous formula. That's how it works, and you can actually play with it this way, assuming you know the Bernoulli numbers. But what I really want to do now is actually do that integration technique. How can I use this formula to explain why turning the handles of integration, ignoring plus c's and all that, actually does do the correct thing? We're set to do that now. Okay, let's get to that weird, wild, crazy, wacky integration formula that takes you from pk of n to the next one, pk plus 1 of n. And the first step was to multiply everything through by k plus 1. But if I do that, I can see it's going to be very nice for us here, because k plus 1 times what I've got so far is actually just that numerator, n plus 1 plus b to the k plus 1 minus b to the k plus 1. Grand and good. The next step was to integrate with respect to n and ignore the plus c's. Well, I'll be thorough. I won't ignore the plus c's. I'll write it in. So the integral of this, k plus 1 to the pk of n, with respect to n, will be the integral of this with respect to n. That will be 1 over k plus 2, n plus 1 plus b to the k plus 2, minus integral of this with respect to n is k plus 1 times n, and then there'll be a plus c. Great. Now, you might be wondering, this is not really the binomial coefficients, James, because I'm really doing this weird thing of saying BR is the same as the BR. But if you were to expand this out and do the individual integrations, and then you can bring it back together again, you will get that. So actually, that is speaking truth right now. All right, so what have we got going on here? So that tells me What am I seeing? Actually, what I'm seeing right now, this is very close to the next formula. I'm just missing this sort of equivalent stuff. So let me put that in. I want n plus 1 plus b to the k plus 2 all over k plus 2. I want a minus b to the k plus 2 there. So let's put it in. Let's undo putting it in. Plus b k plus 2 over k plus 2. Then I've still got a minus b k plus 1. Whoops, b k plus 1 times n. I've still got a plus c. And that is actually my next formula. All right, so what is this saying? This is saying that my next formula, let's write it out this way, my next formula is actually the integral of the previous formula multiplied by k plus 1, just like I was doing in that very first video. Then there's this n term. Let's put this, I want that by itself, so I'm adding stuff to that side. Okay, it's plus bk plus 1 of n, and then subtract this constant stuff. There's a constant c in this constant stuff, minus, I think I'm going to just erase this part of the board here so I can get some room. Oh, I don't need that. I can do that. Minus bk plus 2 and k plus 2 and a plus c. Bingo, that's what we've got right now. We have just established that the next formula is the previous formula multiplied by k plus 1 integrated with extra features floating along. All right, okay, so now can I deduce what the extra features have to be without really knowing what the actual individual numbers are? Which C are we playing with? What are these numbers BKs? Do I actually need to know them? The answer is I don't. Because remember, from the very first video, we proved that pk of n is always a multiple of n. So it's always going to start with like something times n, and something times n squares, and n cubes, and n to the fourth. So it's going to be some polynomial, n's and upwards. Which means if I take the integral, this is going to be some polynomial with n squareds, n cubes, n to the fourth, and upwards. Because the integral of n is half n squared, I'll have n squareds and higher. Alright, so this involves only n squareds and ups. Great! Oh, if it only involves n squareds and ups, that means, okay, there is no constant term. So whatever c turns out to be has to be that which makes that 0, because I know this formula has no constant terms. Bingo, so the plus c must be whatever it is to make that be 0. Great. All right, and then look at this. I need a bk plus 1 to the n. I don't know what bk plus 1 is. I don't know what it is, except I do know these polynomials. They all have the property that bk of 1 is 1. That is all the sum of all the individual coefficients made up to 1. These have got n squareds, n cubes, and so forth up high. So this got a whole bunch of coefficients, and I'm missing the n coefficient. I don't know what it is, but just choose whatever number that works to make all the coefficients add to 1. So I don't actually even need to know what these Bernoulli numbers are. I can look at what I've got and say, oh, what's the coefficient I need to add up to 1? To get all the coefficients to add up to 1, that must be that Bernoulli number. Whoa, that was the integration technique we were doing earlier. It is crazy, but there it is. It all actually falls into place from this beautiful, beautiful formula. Faulhaber's beautiful formula. It is stunning. Okay, suppose for some jolly reason you do actually want to work out those Bernoulli numbers. Just have fun, go for it. In fact, here's a lovely way to go about it. Let's use this formula, but let's tweak our thinking about how we interpret it. Think of this as pk of n is n plus a number, b plus 1, that gets raised to the k plus 1th power. Take away that b to the k plus 1, all over k plus 1. So think of this as the binomial theorem being applied to n and another number. The other number happens to be b plus 1. Now the thing to note is that these summation formulas have a 0 constant term. They're all multiples of n, so the constant term is 0. And I can kind of see from here what the constant term has to be. When I do the binomial expansion here, I'll get b plus 1 to the k plus 1 is the constant term coming from here. It must cancel with the only constant term I've left up the top as well. So we must have that this term, b plus 1 to the k plus 1, must match this term precisely. Oh, great, grand. And we know this formula is valid for k greater than or equal to 1. At k equals 0, we're off by 1, but we'll start from there at k equals 1 and onwards, because this is now saying magical things. All right, here goes. So let's apply that recursive formula right there. Now we do know that b naught is 1. That's something we actually did in this video for sure. To get to the next one, let's actually choose k equals 1 in this formula. So b plus 1 squared should equal b squared. Now I'm saying squared, but that's really b2. In fact, if I were to expand this out, b squared is b2 plus twice b to the 1th power times 1, b1, plus 1 squared, 1 equals b2. Whatever the b2s are, they cancel. So I get twice b1 plus 1 is 0. Oh, b1 B1, oh wait, all right, B1 better be negative a half. Whoa, whoa. Now let's actually look at this formula for k equals 2. K equals 2 tells me that b plus 1 cubed equals b cubed. Well, actually, let's do this, formally b cubed is really b3 plus 3 times b squared times 1 plus 3 times b to the 1th, b1, times 1 squared plus 1 cubed is 1 equals b3. Whatever b3 is, doesn't matter, I get 0. So I'm seeing that 3b2 plus 3b1. b1 was negative half, so minus 3 halves plus 1 equals 0. So 3b2 is a half. B2 is a 6, just like I said earlier. Beautiful, beautiful. And if you like to do the next one, I bet you see that B3 is 0. B3 is 0. And if you want a little challenge here in playing with this recursive formula, can you prove that not only is B3 0, B5 is 0, B7 is 0, that B odd, any odd number beyond 1, is sure to be 0. A little property of the Bernoulli numbers. Grand, beautiful. Look at all this. Playing with these sums of powers formulas is just stunning. Lovely, intuitive, a lovely, curious little recursive formula there. You've got to love this work that went on 400 years ago. This is amazing stuff.